طيب here شباب in this example for the heat exchanger we have a refrigerant 134A is being cooled actually by water in a condenser. So the condenser شباب is a kind of the heat exchanger. So that means we have a heat exchanger in this case. And in this heat exchanger, he said we have hot refrigerant is coming. So we have the hot refrigerant inside is coming inside this tube. So this is the refrigerant 134A. He said he numbered it as 3 here. So this is 3 coming at 3 cross section 3. This hot refrigerant is coming with flow rate, M dot refrigerant is equal to 6 kilogram per minute in this case. And the refrigerant is coming at section 3 by pressure 1 megapascal. So V3 is equal to 1 megapascal and temperature is equal to 70 degrees C. This refrigerant is leaving at cold temperature at cross section 4. T4 is 35 degrees C. And they said this refrigerant is being cooled down using a cold water. They said the water is coming here at cross section 1 at pressure B1 is equal to 300 kilopascal and temperature T1 is equal to 15 degrees C. And they said this cold water is leaving at cross section 2. So this is 2. So this is 1. This is 2, this is 3, this is cross section 4. Okay, so it is leaving at cross section 2 at higher temperature T2 is equal to 25 degrees. He said neglecting the pressure drop within the system, neglecting the pressure drop, that means B3 will be the same as B4 is equal to 1 megapascal and B1 is the same as which is 300 kilopascal. Okay. Now I have pressure, temperature, and at all point in this case. And he said we need to calculate the required mass flow rate of water to cool down this refrigerant to have an outlet temperature equal to 35 degrees C, and the heat transfer from the refrigerant to the cold water. So we need to calculate, in this case, the mass flow rate of the cooling water, and we need to calculate also the heat transfer absorbed by the cold fluid, which is the water in this case, Q dot by the water, or Q dot cold in this case. Okay. طيب, let's apply the mass equation, شباب. So we have in this case M dot hot, M dot 3 will equal to the same as M dot 4, and in this case M dot 1 will be the same as M dot 2 in this case. But we cannot get anything from it. So let's apply the energy equation, summation if M dot inlet H inlet is equal to summation of M dot A. Or we have reduced this equation to M dot hot, which is the mass flow rate of the refrigerant, multiplied by the difference in enthalpy. It will be H3 minus H4. That is equal to mass flow rate of the cold fluid M dot water multiplied by T2 H2 minus H1. In this case, we don't have external heat transfer, so Q is equal to 0 in this case. So I don't need to add here Q. Okay, so this term actually is 0. So we have M dot refrigerant multiplied by H3 minus H4 will equal to M dot of the cooling water multiplied by H2 minus H1 in this case. But we need to calculate all of this enthalpies at the different point. We have pressure and temperature at all points. So in this case, at point 1, pressure B1 is equal to 300 kilopascal, and temperature T1 for the water is 15 degrees C. So pressure and temperature will be given. So I will go to table A5, and I will get with the pressure, I will get the saturation temperature. You will find this actually temperature T1 is less than the saturation, so the state is subcooled. Subcooled, I have to use table A7, but actually when you go to table A7 with this pressure 300 kilopascal, which is 0.3 megapascal, so in this case we don't have table in the subcooled table. So what should we do? So I will go to actually with the temperature T1 equal to 15 degrees C, I will go to table A4 and I will assume H1 will equal to H fluid in this case. H fluid, H1 which is equal to H fluid at 15 degrees C will equal to 62.9 kilojoule per kilogram. Similarly, actually at pressure P2, which is 300 kilopascal as well, and T2 is 25 degrees C. Also, it is a similar case. So in this case, the temperature will less than T saturation. So this subcooled, but we don't have subcooled table. Then with this temperature, T2 equal to 25, I will go to table A4, and H2 also will equal to H fluid at 25. H fluid at 25 will equal to 104.83 kilojoule per kilogram in this case. And this is actually the enthalpy H1 and H2 for the water in this case. Okay. What about the refrigerant? So refrigerant is coming at cross section 3. So B3 is equal to 1 megapascal. T3 is equal to 70 degrees C. Pressure and temperature are given. So I will go to table A12 with this pressure, and I will get the saturation temperature. You will find this temperature is greater than the saturation temperature. So in this case, I have to use table. Which table? Table A13 in this case. With this pressure and temperature, we can get H3 from table A13. You go to table A13, it will equal to 303.85 kilojoule per kilogram. And this is the enthalpy H3 in this case. Point 4, B4 for the refrigerant, 1 megapascal. Temperature is equal to 35 degrees C. I will repeat the same. Go to table A12, get the saturation. We already got the saturation at the same pressure from step 1. But you will find this temperature T4 is less than the saturation temperature. So the state is subcooled in this case. Subcooled, and it is the refrigerant. So in this case, we don't have subcooled table for the refrigerant. So in this case, we said we can take this temperature T4 and go to table 11. Then we can say actually H4 will equal to H fluid at this temperature. And H4 will equal to 100.87 kilojoule per kilogram. And this is actually H4. Now we have H1, we have H2, we have also H3, and we have H4 in this case. Now we can just substitute to this equation, H3, H4, H1, H2. The mass flow rate of the refrigerant is given 6 kilogram per minute. Okay, so we can leave it in kilogram per minute, then we can get the mass flow rate of water also in kilogram per minute. If you calculate the mass flow rate of water, it will be 29.1 kilogram per minute in this case. So the mass flow rate of water will equal to 29.1 kilogram per minute. So if we substitute mass flow rate of water 29.2 kilogram per minute in this case. Okay. But we need to calculate also the heat absorbed by the cooling water, which is Q dot cold. So as we said, Q dot cold will equal to the mass flow rate of the cold fluid, which is water, multiplied by the difference in enthalpy, which is H2 minus H1 in this case. We got the mass flow rate of cooling water. It is equal to 29.1 multiplied by H2, which is 104.83 minus H1, which is 62.9. Then we can calculate this. It will be calculated in kilojoule per minute in this case. 1218 kilojoule per minute. But we need it usually in kilojoule per second, which is kilowatt. So we can convert minute to second. So we can just divide here by 60. Then we can calculate this value in kilojoule per second, which we call it actually kilowatt in this case. Let's end up with those steady flow devices with the last kind of steady flow devices, which is actually pipe and duct flow. when we have general flow in a pipe or a duct. Pipe which have a cross-sectional area, circular cross-sectional area, the area is equal to pi over 4d square. Duct, when we have actually a kind of rectangular or a square cross-sectional area, we call this as a duct in this case. But let's say we have general flow inside a pipe or a duct or something. Actually, this kind of flow inside a pipe or a duct have different application, like the transportation actually of oil. Before exporting this oil, we just transport the oil from the field up to actually the big tanks or big header. Then in this case, we can just put it in barrel and later on we can export it. But first of all, we have to have a kind of a line of transportation, and also there are some companies actually for transportation of oil through pipeline from one place, from one country to another country or something. So this is a kind actually of fluid transformation, or a kind actually of a flow inside a pipe or a duct in this case. Flow inside the duct also like the air conditioning system, central air conditioning system. We have actually air handling unit, which actually reduce the temperature of the air through a refrigeration system. Then we pass the air actually inside the duct. Then we can distribute actually to the different room inside the same building. So if you look at the air conditioning system, you will find the air is flowing inside the duct. Usually it is a kind of rectangular cross-sectional area duct. Also, we have some application for flow in pipe or duct, like small application, like when we have air dryer. The hair dryer actually we have flow is passed inside actually a duct, pipe or duct, and we have a fan, and then actually we can have electric heating coil to heat up the air inside. And it is the same idea actually of electric heater. When you have electric heater during the winter or something, we pass actually the air inside actually a pipe. This pipe actually is covered by electric heating coil. Then in this case, when the air is passed through the electric heating coil, it gets heated in this case to heat up the room in this case. Now let's consider actually a general flow in pipe or duct, whatever the application, oil transportation, air conditioning system, transporting cold air, or if we have actually hair dryer or we have electric heater, anything. Anyway, we have a flow inside a pipe or duct. So in this case, we may have a kind of fan or shaft bar in case of air dryer or something. So if we have something like this, that will mean have actually shaft power input to the system in this case. In some cases, actually, in transporting, let's say, oil in cold weather or something, so usually they have electric heating coil just actually coiled around this tube in order to heat up actually the flow inside. So for winter in countries like Canada or something, the temperature gets down much below actually the 0 degrees Celsius in this case. So to transport oil or to transport any fluid in this case, we have to have a kind of electric heating around this tube in this case. And if we have electric heating coil, so it depends on the case. If any application we have electric heating, then we have electrical input power in this case. If we have shaft power mixing to fluid or forces the air inside air dryer or something, then in this case we may have shaft work in this case. But in case of transporting, let's say, hot fluid, so usually hot fluid is subjected to the environment. So in this case, we may have actually a kind of heat loss to the environment in this case. Or also if we are transporting cold fluid, like as a cold air in case of air conditioning system, so usually we have air inside, so we may have actually heat is transferred into the system in this case. So this is a kind of general flow in pipe or duct in this case. So whatever the application, it will be given for you. Then in this case, we can just draw our control volume and look at actually the surface of this control volume and look at the energies and the mass transfer through the system. So let's say the flow is coming to this general pipe or duct at section 1 and leaving at section 2. So in this case, we can apply the mass equation. So mass equation, this is actually a single stream steady flow. So in this case, we can say m dot 1 at the inlet section will be the same as m dot 2, which we call it actually as m dot engine. And then we can say density rho 1 A1 V1 is the same as rho 2 A2 multiplied by the velocity V2, and it is actually equal to the mass flow rate at any cross section. This mass flow rate is equal to the density multiplied by the volumetric flow rate at any section. This is volumetric flow rate at the outlet, and this is the volumetric flow rate at the inlet section. Okay. And density is equal to 1 over a specific volume. So it is equal to the volumetric flow rate divided by the specific volume. This is the volumetric flow rate. So rho 1 is 1 over the specific volume, and A1 V1 is the volumetric flow rate at the inlet section. Rho 1 it is 1 over a specific volume V1. This is the same as volumetric flow rate V2 divided by the specific volume V2, and this is actually equal to the mass flow rate in general. Let's apply as well the energy equation for the first law of thermodynamics. We have actually steady flow of single stream. Then we can just write down Q dot minus work dot will equal to M dot multiplied by H2 minus H1 plus V2 squared minus V1 squared divided by 2 plus the change in potential energy G multiplied by delta Z. We don't have a change of elevation from the inlet to the outlet. We can neglect. Also the same cross-sectional area, so we assume we don't have significant change in the velocity, so this term will be 0 in this case. Or we can say Q dot minus work dot will equal to M dot multiplied by the change of enthalpy H2 minus H1 between the outlet and the inlet section. Okay, so this is the general equation for flow in pipe and duct. This term heat transfer or the work, in this case those two values will be 0 if not given or required. So we may have in some application, we may have heat transfer, we may not have it. In other application, we may have work to the system or we don't have it. So it depends on the case in this case. Okay. So if they are not given or required, they will be 0. But this delta H, how we can calculate it? I will just stress on this again. We say delta H, if the working fluid is steam or refrigerant, 134A. Then in this case, I will be using the tables. The condition at the inlet and outlet section will be given. Then I can use the table to calculate H1 and H2. And in case of gases, we said we have two cases, variable specific heat and constant specific heat. Constant specific heat, which is Cv delta T. This Cv is calculated based on the average temperature T1 and T2 from table A to C. Or we can use actually tables from A17 to A25. This is actually, we call it in this case, the variable specific heat analysis. This is the constant specific heat analysis, delta H, Cv, delta T. Variable specific heat analysis we can just use the values from table A17 to A25. Okay. But let's see an example and see how we can solve general flow in pipe or duct in this case. Okay. Type here in this example, you can look here. We have an electric heating system. So we have an electrical heater in a house that is existing in a house, maybe in winter or something, to heat up the house of a single duct. So we have flow in pipe and duct with a resistance heater. The idea here, he said, we have an electric heater. We force the air to go actually through the electric heater. The idea of the electric heater, we have an electric heating coil. So we have input electrical power in this case, which is a high resistance coil. So the heat will be, the electrical work will be converted to heat. This heat will be absorbed by the air. Then at the end, actually, we can have actually hot air is leaving this electric heating system to heat up the surrounding air inside this room. He said we have electrical power, input equal to 15 kilowatts, the electrical power. We have also wire is lost to the surroundings, so Q dot is equal to 200 watt. This is watt, this is kilowatt. Okay. He gives the inlet condition of the air, so let's say actually this is cross section 1 and this is cross section 2. He gives here the temperature T1 at the inlet, which is the room temperature 17 degrees C. V1 is equal to 100 kilopascal, and he said the volumetric flow rate at the inlet section. So the volumetric flow rate is different from the inlet to outlet. Okay, but mass flow rate is the same. Volumetric flow rate is not conservative property. So the volumetric flow rate is 150 meter cube per minute. Please take care about the unit in this case. and he asks us to calculate the temperature of the air actually leaving this electric heater. Okay. Right, first of all, let's calculate the mass flow rate. So we said m dot is equal to density multiplied by the volumetric flow rate. This is at section 1 or at any section, so rho 1 V1. And we said rho 1 is 1 over the specific volume, so it will equal to V dot 1 divided by the specific volume V1. Type specific volume V1, here the working fluid is what? Working fluid is air. Which device I'm dealing with? General flow in pipe or duct. He said this, we have a flow in this duct. Okay? Right, in this case, the specific volume for gases, we have the ideal gas equation of the state PV equal to RT, or the specific volume will equal to RT divided by V. The specific volume V1 will equal to RT1 divided by V1. Type R from the table for air, I think you remember this value, 0.287, or you can just get from table A1. Multiplied by T1, which is 17 plus 273, divided by B1, which is 100 kilopascal, because this one is in kilojoule per kilogram. So keep this as 100 kilopascal. You can calculate this. It will equal to 0.832 meter cube per kilogram in this case. Okay. So can we just calculate in this case volumetric flow rate? This is the equation that we are going to apply. So in this case, the mass flow rate will equal to V dot 1 divided by specific volume V1. V dot 1 is 150 meter cube per minute, so just divide by 60 to convert it to meter cube per second, divided by V1 0.832. If you calculate this, it will equal to 3 kilogram per second in this case. Okay. Type to calculate the temperature. Temperature is related to the energy equation in this case. Okay. Type this is the energy equation, Q dot minus work dot equal to M dot multiplied by delta H. This heat transfer, Q dot, this heat is lost, so it should have negative sign, and it is equal to 200 kilowatt. We said all of these terms in the equation should be in kilowatt, the unit. So this is in watt, 200 watt, which is 0.2 kilowatt with negative sign. But here we have minus. This work is input to the system, so it should have negative sign. So we have negative here, plus this work is equal to minus 15 kilowatt. So minus will be positive, in this case positive 15 minus 0.2, which you can see here substituted here, 15 minus 0.2. That should equal to M dot, which is 3 kilogram per second, multiplied by delta H. The working fluid in this case is air, which is gas. Okay, so we have either constant or specific heat analysis, either we can say delta H is equal to CB delta T, and this CB we can just get from table A to C for air. At the temperature here we need T2. T2 is not given, so in this case we can get it at T1. When you go to the table to get CB, it will equal to a kind of 1.005 kilojoule per kilogram. We have delta T in this case, which is T2 minus T1. T1 is 17, we can just leave it in degrees C in this case. Then we can calculate T2 in degrees Celsius. So T2 will equal to 21.9 degrees. And this is the outlet temperature from this electric heat. It will be a kind of 23 degrees C. And the inlet temperature in the winter was about 17. So the electric heater can raise the temperature from 17 up to 22. So a kind of 5 degrees C rise in this case. But this is if you are following the constant specific heat analysis. If I want to use the variable specific heat analysis approach, we just can say this is air, so we can use table A17. So at temperature T1, in this table, the temperature is listed in Kelvin in this table. Just to convert it to Kelvin before going to table A17, then we can get the value of H1. Substitute here, in this equation we have everything, then we can get H2. Take this H2, go back to table A17, then we can get T2 in this case. Inshallah, in your exam or something, I will just tell you which approach you have to follow in this case. Okay. By this, we are done with all of the steady flow devices. Inshallah, next time we'll be starting talking about the unsteady flow to end up with this shape.